Thank you. So let me just share the slides, and I will begin with just a few slides as an opener, then I'll pass over to Dave for the runner, and then I'll take over again as we show the UI. So one of the things I love about Apache Beam is this core vision that it allows us it should have developers being able to develop in the language of their choice, building pipelines using a very expressive model to be able to then take that pipeline that they've created and then run it on the execution environment of their choice, whether that's Dataflow, Flink, Apache Spark, Samza, etc. In terms of the language and the model and the building of the pipeline, what does that look like? So at a very high level overview, there's three core primitives. One is the P collection, which is an unordered set of data for input and output. Our P transform, which is the data processing operation that we can do on one or many P collections. And then a pipeline. The pipeline strings together the transforms of the P collections to build us the directed acyclic graph of computation that we would then submit to the service. At the bottom, there is a very typical one. We have a bounded database table that we are going to run a read transform against. That transform will generate our P collection, which another transform will then take to enrich and shape the schemas, etc., ready for the right transform to output to a database table. So using those primitives, actually very easy to start building up quite sophisticated pipelines, not just in terms of movement and shaping of data, but also in terms of enrichment and analytics that you can do within the stream. And one of the very cool pieces about Apache Beam is that the batch or stream processing, it deals with both, and there's very little to change often in terms of the core business logic when you're moving from one to the other. To show that and show a little bit of how a pipeline comes together, we'll just walk through this one example, which is in batch mode, and then next we'll do a small example in stream mode. I actually do my coding in Java, but we've got Python here, so it is quite nice and neat. And but even in Java, it's actually the Java one is not much worse, but obviously a little bit more verbose. In the Python, the one interesting thing when you're looking at this that may be unfamiliar is the pipe operator. So P here stands for a pipeline, and the pipe operator you see next to it has been overloaded to say p.apply. So that pipeline means apply to the pipeline this transform. So we will add this node to our pipeline. The use case, let's imagine we have files that are coming from our online systems and our bricks and mortar stores. So let's imagine we're a retailer, and what we want to do is count the number of items that are being sold. So there's two things that we need to do. First, we'll need to read those files in. For our store sales, we will use the primitive read from text, and this will actually allow us to consume, to process those files and bring them into a P collection. We will then do a mapping function on that data. So what the map is doing, it will extract the item ID from the row of information that we have. Because we have two sources, we're going to actually generate two P collections, so store sales and online sales, which are doing exactly the same thing, just with different sets of files. Now that we have these two P collections, we need to bring them together. Because the item within the P collection is the same, it's this item ID, we can actually use a flatten operation. So beam.flatten, a primitive of the Beam model. This will bring those two P collections together. And then we're going to do some analytics. So first, we will do a combine count per key. So what this will do is it'll count the number of items uniquely within that item ID. That will generate an output which we send to our final analysis, which is top. So give us the top 10 items that have been sold. The result of this we output to BigQuery in this example, data warehouse, but this could go to Pubsub or files, etc. So let's take this pipeline. So with that simple bit of code, we've written a interesting processing pipeline. Let's convert this into a stream pipeline. Well, there's very little we need to change based on our code. First of all, we need to change our sources. We now move from files to an unbounded stream source. In this case, Google Cloud Pubsub, which is Google's publish and subscribe API. That allows us to take an unbounded source of data that we are processing. Next, the rest of the logic remains fairly similar, with the exception of a windowing function. Because we've now moved from a bounded data source to an unbounded, so this is going to continue sending streams, we need to understand when to materialize data. So when do we finish our counting? In this particular instance, we have a window into fixed windows of 10. So this will create discrete windows of 10 seconds. So every 10 seconds, we're going to be doing a count and pushing the results down. So very little needed to change. And again, important to note that the code we're writing essentially is declaratively describing the graph of computation that we want to build. So that was covering some of the SDK and the primitives. What about the execution engine? So where do I run that that graph that I generated? And for that, and for the bulk of obviously today, we're going to be using Google Cloud Dataflow. So with that, I'm going to hand over to Dave, who's going to go through the Dataflow runner. And then after he's done that, we're going to go and see a live example and walk you through the monitoring interfaces and some of the debugging that's possible to do, as well as looking through a retail sample. Over to you, Dave.
Cool, thanks, Reza. So yeah, basically, well, first, my name is David Sabather. I'm from Google. I'm actually the EMEA solutions lead for streaming analytics. So part of our solutions involve Dataflow and Pubsub, as Reza mentioned. So I will go through the runner and also some of the features before I hand over to Reza for the cool demo about retail. So basically, Dataflow is the Google Cloud runner to facilitate running your pipelines, your Apache Beam pipelines, right? So what Reza was describing before, the way you will implement the pipeline with the SDK, you need to actually have a platform to execute that, right? So that's what we actually bring with Dataflow. And it's not just that, but I also implements and offers a set of features and actually is integrated with our GCP services like security and so on. So Reza, can you move to the next slide, please?
Sure.
Thank you. Next one, sorry, that's, I would go into the features straight away because it's about the time. So basically, we have here the set of features that we have in Dataflow. So basically, as I mentioned, we integrate with features like security with key management service, KMS. I will cover that briefly. Monitoring and logging, which will be covered by Reza, and also networking and identity access management, right? But apart from that, we have a nice set of features, which I will go through, like the streaming and shuffle engines, graph optimizations, and a few other things. So Reza, if you can move to the next slide, please. Again, next one, sorry, a bit of animation there. So basically, the way the Dataflow service works is you first implement the pipeline in whatever SDK and code that SDK you're using, being Python or Java. So what you do is just you submit your pipeline code to the regional endpoint, which is the job manager, and at the same time you stage that code into GCS. So basically, the endpoint, what it's doing is actually controls the job and actually also keeps some metadata about the job status and things like that. And also what it does, it deploys that code into the actual infrastructure and provisions the infrastructure to run and execute your pipeline, right? So basically it provisions a bunch of workers or virtual machines to do the work. What is important as well here is that together with the code, we provision a representation of the DAG, of the graph that we are going to compute with a set of peak collections, peak transforms, and the inputs and outputs, right? So that is also being used by Dataflow Runner to introduce a set of optimizations that I will briefly describe here. But the whole point here is that we expose a regional endpoint for you to interact with the service, and then that service also provisions the infrastructure for you automatically. So again, it's a fully managed service. You don't need to worry about how to provision these things. We do all for you, and then we also provide security and logging and monitoring. So Reza, can you move to the next one, please? Cool. As I mentioned, we have what we call the regional endpoint. That's a control plane. That's on where we keep the status of the jobs, and we also interact with the API. So that's on where you submit the job, either using the G-Cloud command tool, using APIs directly with your SDK libraries, for example, with Terraform, with Airflow, whatever other tools you're using to integrate and submit your jobs, but also within the UI, right? So the first thing is, by default, if you're not provisioning a region, by default, we're using US Central one, but you can specify anyone or any of the regions where we have the endpoints available. We're rolling out every time and again new regions, so we're covering more and more regions as we speak. Then also you can specify where your workers are actually crunching the data. So basically that's defined at the zone level. So region, I don't know how familiar you are with GCP, but we have a region, and then within a region we have multiple zones, so availability zones. The endpoint is at the regional level, and then the zone where the workers are running is zonal. So you either leave that empty, and by default it will allocate the workers in the region where is enough capacity for that. Otherwise, you can override that and specify your own zone. Having said that, you can actually specify the zone in a different region, because sometimes there may be reasons that you need to actually run the job somewhere else because of security, compliance, or actually data locality, that you have your data in a particular zone or region on where we don't have an endpoint, or where you don't really need to deploy that, so you can still do the processing there, right? So that's also gives you a lot of flexibility. So that's the way we interact. Yeah, there's a question here about the quick labs. Yeah, it's a different instance, Vijay. So you need to go into the ce.quick labs. So that's the one we are actually enabling the labs for you, because the other one is the public one. So you need to have credits and things like that. So if you register into the CE one, you will be able to directly access the labs that we will present. Okay. So yeah, continue with the infrastructure. So another level of integration we have with GCP is about identity access management. That's really important when you are running production workloads in the cloud. You really need to ensure that you are authenticating and authorizing certain users, right? In GCP, we have the concept of service accounts. So basically, a service account is a non-human Google account that you use to actually authorize and authenticate your workloads, and then being able to access certain services, right? So basically, when you enable the Dataflow API to be able to submit your Apache Beam pipelines, you actually get two different service accounts. The first one is the Dataflow service account that's used to actually create the workers and also integrate with the monitoring and logging from GCP. But also you have the controller service account that's actually used to access your IO, like Pubsub, BigQuery, and so on. If you are not specifying any service account, typically that service account is the GCE, the Google Cloud Engine default account, which in theory has access to all these services. But you can actually have more granularity, and for example, in your enterprise company, if you actually need to be more specific about which service account to use, you can actually specify that when you submit your jobs. At the same time, you have a third service account, which is used to control who can submit pipelines to the API, right? But by default, you have two, and you have a third one as optional if you want to control and authorize who can submit these pipelines. So that's on the infrastructure and the identity access management. Can we go to the next one, please, Reza? Thank you. So then now we're going into the actual features about Dataflow as a runner, right? So the first one is about graph optimization. So basically here, what we're doing is, as Reza described it, we are actually executing the set of transformations on your P collections as a pipeline. Basically what happens here is that if we were keeping, in some situations, some of these transforms, we will be materializing the data in every single step, right? Sometimes that's, well, sometimes that has an overhead because you actually need to either shuffle or actually persist that in disk, and that has an overhead in the end-to-end time. So what we're doing here is whenever is not required to actually do that materialization, we can actually combine and fusion these transforms. So basically what we're doing is, let's say we have two P transforms that they are mapping elements one-to-one in different stages. We can actually fusion these two because there is no state that is required to be kept between these stages. That typically happens where we're not doing any shuffling, anything on where we are reorging, grouping by key. So I'm actually doing aggregation, so kind of the reduce phase, right? Only we're doing mapping, so we can actually fuse these things. That's really efficient because actually performance is one aspect, that also costs, because if you had to actually keep that state many times, the amount of storage and memory required will be much higher. So what we're doing here is introducing some optimization to not just performance, but also for cost optimization. Okay, so we can do that on stages, so transforms that are happening sequentially, and also that are the ones that are happening in parallel. Okay, so thanks, Reza. Can you move to the next slide, please? Thank you.
It's just being a bit slow. There we go.
No worries. Cool. Another level of optimization is what we call combiner lifting. So here, what happens is what I referred before about shuffling and then reducing, which basically what it means is that we actually aggregate certain elements by key. What we're doing here is that in the case of certain aggregations, we can actually do these aggregations locally at the different workers before shuffling the data to centralize to obtain the global aggregates. We typically, I think we're doing that by default only on the batch jobs, because on streaming it's not giving enough advantages, because in streaming the combines and the triggering that we're introducing, it needs to produce the aggregates quite often. So there is not really, is more of an overhead of the combiner lifting. But for batch is introducing a really nice set of optimizations because it's actually pre-aggregating the stuff before shuffling it. And we know that any shuffle between workers or distributed systems is always super costly. So that's another nice feature for graph optimization. So I think that covers graph optimization. Next one is about dynamic work redistribution. That's again a nice, powerful feature in Dataflow. What this typically does is, and that's common to any distributed systems, is you may have hotkeys or things like that are actually they're putting a latency on some of your workers. So basically, what we have in Dataflow is able to detect workers that are actually taking longer than others, and is able to split bundles. Bundles is actually set of elements that are being processed in certain workers. Is able to split these bundles in further chunks and then redistribute these across idle workers. So basically what it's able to do is redistribute the job to actually take advantage of the infrastructure, right? So because what we don't want here is, let's say you provision a job and you have hundreds of workers, but only half of them are idle, busy, because the other ones, they completed the job. What you want to do is actually maximize the capacity available, right? So you want these all workers to be busy crunching the data. So again, that's available and fully automated as well. We also provide a set of hints, so you can actually detect hotkeys and then apply some level of logic to actually help give hints to the worker to actually split these bundles in and then evenly distribute. But yeah, that's the key feature here. Thanks. Reza, can you move to the point? Thank you. So this one is about shuffling service. I briefly mentioned shuffling before. Again, very costly. Also, shuffle needs to keep state, and as I mentioned before, between stages. So until we introduce the shuffle service for batch and actually for streaming, which is the next slide, we were keeping that state and then the processes associated to that within the workers that were crunching the data, right? So that implied a set of things. First is that state was kept locally in each of the workers. So we had extra requirements in terms of storage and CPU. So we had extra cost there. And actually also on the rebalancing and then auto-scaling features, because that state had to be replicated across the workers. By introducing this service, actually we're centralizing that, which means that first we are reducing the extra cost associated with with these extra processes that are required on each of the worker. So we centralize that. So what we are also introducing is more flexibility in terms of rebalancing the job. So when we need to scale up or down or rebalance the workers, is much easier with the shuffle service. And because of all these extra features, and in majority of the pipelines is introducing some performance improvement, this service has a small cost associated, which typically what we do with customers is you test your pipelines and then you see whether that service is worth for you or not in terms of introducing performance optimizations, and also to give you more warranties about the scalability and the flexibility you get there, right? But that's more about testing for your particular pipeline and see whether that service works for you, which is actually when you submit the job, is a flag that you enable when you submit your batch job. Okay, so that's on the shuffle service. Reza, next slide, please. Equivalently, we have the same concept as a streaming engine. So that's similar concept, but for the streaming pipelines. In this case, apart from shuffling, what we are also centralizing is the window stage, right? As Reza mentioned, the main difference, or one of the main difference, when we are using unbound streams in streaming engine in Dataflow, is that we need to keep the state of the window, and then when we trigger and emitting the results, so that state is also stored in that state, right? So what we're doing here is also centralizing that. What is important here is in terms of is autoscaling, it gives you even more flexibility, because as you could imagine, when we're running streaming jobs, you may get actually an increase in volumes over certain periods, which is more unpredictable than if you are, for example, using a batch job, because you know it's bounded and you know when it's starting and when it's finishing. With the streaming, is more unpredictable, so you need to have a more flexible autoscaling feature there, right? So what the streaming engine is giving you is more flexibility there, because otherwise, because of that state, you need to provision disks in a particular way if not using the streaming engine. But with the streaming engine, you have more flexibility with the workers. The workers are basically more nimble. You need less storage because of that state, and shuffling is kept centralized, right? So again, nice feature. Again, that's also important to test your own pipelines, because it really depends on your logic whether you're going to benefit or not. And then again, it has an extra cost associated, so you really need to evaluate whether that feature gives you good features, good performance as well. Okay, so that's for the streaming engine. Next slide, please, Reza. Yeah, that's about, as I mentioned, fluid autoscale feature, having nimble workers with less, let's say, static storage, because you need to keep the state across all these physical disks. It gives you more adaptability when you have either an increase in load of a number of events arriving when you are streaming and processing your data, when you're going high or when you're going low, which is also important, right? What you want to do, like the rebalance of your workers, you want to make sure that you are maximizing your infrastructure, so you wouldn't have idle workers. Basically, what it means with autoscale is that when you don't need to, the workers will be actually shut down, so you don't need to worry about paying extra money for resources that you are actually not using, which is really important as well with these distributed systems, right? Cool, so that's on the autoscale. Next slide, please, Reza. Yeah, so that's about updating and live development software, SDLC, sorry, so developer lifecycle. When you need to update your pipelines under certain conditions, you can actually do that with maintaining the job running, and that's obviously applicable to streaming pipelines that they are continuously running. What you can do with a flag is actually update your existing pipeline with a new code set. There are certain restrictions there, and actually, as when you are submitting the job, there is actually a check done for you to see whether that's compatible or not. And actually, the nice features that, like for example, if basically when you have these P transforms, you can name the P transforms. But if by these changes you are changing the name of the P transform, you can actually have a transform mapping as an extra feature. So you have quite flexibility there, but obviously there are restrictions in terms of what you're changing, because if the intermediate state changes dramatically as a consequence of your code changes, that will be incompatible. So you will actually need to drain your job and then redeploy that, right? So, but again, when you need to fix things, when you need to update certain features, that is not breaking things and current states, that is compatible, and you can actually keep updating your pipelines live. So that's another nice feature. Cool. Next slide, please, Reza.
Yeah, it's being a bit slow. Let's see. There we go.
No worries. Nice. So we were talking about SDKs, right? So SDKs being a main Java, Python, Go, and Scala as well. But there are other ways actually to interact with Dataflow and with leveraging the Apache Beam framework. So this one we introduced, I think, a couple of weeks ago, and it's in beta now. You can actually run your pipelines using notebooks, Jupyter notebooks, and that's really nice when you are experimenting and then running things, let's say, initially locally, where you're running your Jupyter instance, but also to submit them remotely in distributed mode. You can use Python in the natural way like you will do in other Python distributed frameworks, so that's very nice as well. So it gives you more collaboration as well with your team, so you can share your notebooks like with other environments. So it's another way to interact with Dataflow and submit your distributed jobs, right? Really powerful. Next slide, please. Another way to interact with Dataflow actually is through SQL. Basically, that one is going through the BigQuery UI. You can actually switch the engine from BigQuery to Cloud Dataflow engine and then submit your SQL statements with the same similar syntax or same syntax as BigQuery, but that will run using Dataflow engine. Why? Because sometimes in some instances you might want to ingest data from Pubsub, merge that with BigQuery, and do your experimentations there in an interactive SQL environment, right? So you actually can do that, but rather than triggering BigQuery, which is more for, let's say, interacting with batch and historical data, you can use that to interact with your streaming data, which again, that's the whole point about Apache Beam and Dataflow, right? Is to simplify stream and batch data processing, similar to the notebooks. So that's for the SQL. Again, next slide, please. And ultimately, it's a way to also help people to get on board into Dataflow and use the distributed framework. We have the Dataflow templates. So basically what you can do here is you can either use the existing ones that we provide. So we have 20 plus and they keep growing. But you can also have your pipeline created as a template. So basically what you can do is parameterize that pipeline and then either facilitate teams to submit their jobs without that knowledge about Java, Python, or Go, using and parameterizing through the UI or through command tools, but also to parameterize and productionalize your pipelines, right? So let's say you have certain parameters, and what you really want to do is under certain conditions or certain input parameters, you want to process the data in a certain way. You can parameterize all your pipelines in this way with using templates. And again, that's something that we offer as part of Dataflow. Cool. So that's for this one. Next one, please. So last two, this is about security. We are actually, for enterprises, we can actually enable private IPs. So you are not using any public IP when submitting your jobs, or even when you're accessing any of the other GCP services. So that's super important for certain enterprises, like financial institutions and things like that. So you don't really want to expose any public IP. So we have that feature as well, that all your services are run under private IPs and private networks. So again, nice feature, compatible with things like BigQuery and other services. And the last one is about CMEC. So by default, we encrypt your data at rest and in transit. We use Google managed encryption keys, but actually you can bring your own keys, and we manage them through the cloud KMS, where you provision the keys, and then we use that service to encrypt and decrypt your data. So you can actually use the two options depending on your needs and security needs. Next slide, please. Yeah, and I think with this one, I'm done, and I will hand over to Reza to continue, and then also show you the cool demo we have. Cheers.
Yeah. Thank you very much, Dave. So for this next piece, there are actually 3 features that will actually show as part of our learning for making use of the Dataflow UI. So one is monitoring. So there'll be, we'll go through this in far more detail in a moment. There is also Stackdriver integration. So observability is the first one that we're looking at how we can explore our DAG, the graph of computation, explore what's happening within transforms. With Stackdriver, we can actually set up monitoring and do things like alerts. So if a pipeline is starting to process things slower than normal, fire off an email so we can come and have a look and see if there's some remediation needed. And of course, logging and all the pieces from all of these workers, all generating information, is getting centrally co-located within an environment that we can go and search and explore. So to do this, we're actually going to do a bit of something that I haven't tried before. So we'll see how this works out. And that is to actually walk through a full sample application. But we're going to use the monitoring UI as our documentation for our code. So rather than look at the code and then describe all the different tips and stuff around how to do the what are the best practices in putting the pipeline together, we're actually going to just go through this DAG and try and see if we can understand what the code underneath was doing when it built this piece together. What we are in now is the monitoring user interface. There are 2 tabs that we will be spending time on. One is the job graph. We're going to spend most of our time at the beginning here, and also the job metrics. So these are the high-level metrics, things like CPU, system latency, etc., for the pipeline. Going back to the job graph, one thing, by the way, you'll notice the pipeline is actually called retail pipeline. So a good tip is when you are building pipelines to actually use the app naming option and give your pipeline a name. When you're looking at the list of pipelines running, that's always super helpful. What we're looking at here in this central pane is the representation of the code that I've written, which happens to be in Java in this case. Is a representation of that code and how that looks in terms of the computational graph that it has created. Now, the code for all of this is available. I will share that at the end of this piece. We put this out as a sample application for people to use the code as snippets, etc. Our eventual position that we'd like to get to with that sample application, because for the next version, we're going to add in good practice around CI/CD, etc., is to make it sort of a blueprint for folks to be able to use. So as a starting point, it gives you a lot of useful utilities and things that you would use as good practice when you are building production pipelines, to give folks a bit of a boost when they're starting from that clean slate, when they're first coming to build their first few Apache Beam pipelines. So let's explore this in a little bit more detail. I am going to deselect the step now. So here we are on what you would see when you would first land on a job that is running. There is metadata about the job, for example, it's streaming. The things that Dave were talking about, this is running in the US East 1 region. The zone is US East 1B. It's currently got just one 2-core machine running. There's not much back pressure, even though it's doing 500, 600 messages a second in this pipeline, so we don't need to go over 1 core. So as well as this data, down below on the right, we also see some custom metrics. So within the Beam programming model, there are metrics that you can, as a user, update. A lot of the sources that have been built already have those, so a lot of these are actually coming from the various sources and sinks that I am making use of within this pipeline. However, this particular set of metrics, which is actually a distribution, is one that I have created. So somewhere in my code, I have a JSON parsing function, and if that fails, and I make sure it fails because I have a injector that's throwing in a bad one every now and again, then this value gets updated. And I can see that here. So this is a way for me to externalize information about what's happening within the pipeline to external systems like this UI, and also it can be exported to Stackdriver, which we'll see a little bit later. Okay, so each one of these boxes represents a transform. And within that transform may be one of many do functions which are being processed, are doing transformations against RP collections. So the first one we'll click on is read clickstream. Here there is nothing happening before this step. If I move to the, so now that I've selected this, if I move to the right and look around, we notice that the step has been named, but also we know there is now an output collection. So here we're starting to get information about the output that's coming from this transform. And during this piece, as well as showing these features, it's actually super useful to think of this as how you would go around debugging the pipeline. So when I'm asked to go and either do performance debugging or problem solving with folks, if I can, and sometimes it's not allowed because of privacy, etc., but if I can and they are able to show me this tag, this is where I will spend the bulk of my time, even before I ever look at any of their code. Because I actually often can actually understand what their code is doing just from looking at these pieces and looking at these data points. So one of the ones that we're looking at here, output collections. So we can see that this transform, whatever it's doing, it's at the beginning, so I suspect it's a source of some sort, has processed 1.8 billion rows of data in the time that this pipeline has been running, which I think was about 60 days or something like that. There is about 604 gig of information, so these are lots of elements, but not particularly big elements that are being pushed out from the system. So let's have a dig. If we click on the little icon on the right here, we actually start to get into the specifics of what this transform is doing inside. And okay, so this our suspicion was correct. It is a Pubsub unbounded source, so it's using the publish and subscribe API as a source of data. That information is flowing into the system and it's sending it on to the next stages. I'm just going to close this down now. And then my apologies, as I click on these things, it will move around the screen. So I'll try and pause after each click so that you can reorientate yourselves. In terms of processing the clickstream, so in that step, there's a lot more going on. So there's a lot of business logic embedded here. First of all, we can see that the read clickstream, that P collection is having two transforms applied to it. In code, this would look like P collection dot apply, P collection dot apply. So just doing dot apply twice creates this branch in the DAG for us. The clickstream information that's coming in on one side is going to this transform called store raw data. Now, a very important piece of advice would be that try and name your transforms as much as possible with good names that are easily understandable when we're reading these pipelines. It's the description you do in the Pardue first parameter. The reason it's so useful is because even if you don't really know the code underneath, you can very quickly start doing troubleshooting. And folks like SREs and stuff love it when this has been done properly. It is essentially like putting documentation for your code for others. So here, store raw data. If I click on this, we can actually, again, my apologies, it jumped around. So it's now moved over here. So store raw data. This is being sent to BigQuery.io. Now, this is a very useful tip in streaming pipelines, especially if you can, store the raw information untouched in a format that you can go back to. This is super useful. For example, someone might push some code that's got a bug in it. Things may change upstream that may cause issues. There are all these reasons where it'd be very useful to have a repository of the raw data still available. Now, of course, that's not always viable. If you have very large data sets, it's not always possible to keep a whole copy around, but perhaps you could arrange for a time to live on that environment. So maybe keep it around for a month or a week or whatever is suitable for your SLOs and SLAs. In terms of what we write to this data, because this is such a common action and we do it in multiple places, it's always useful to actually wrap it around an object that is super easy for you to attach metadata to and is common across all of your pipelines. In this particular case, I'm actually going to go to BigQuery very quickly and go to our, actually I will do that in a moment, sorry. Let me close this down now. So here we have, again, so wrap the data with some metadata. I'll actually show a better example of doing that in a moment. So this is our store raw data. Again, I've closed it, so it's jumped around. Apologies for that. Next up, the branch for our clickstream was going into this transform. So the raw data is being written here, but here we are actually doing a JSON to Pojo conversion. So obviously we are doing some parsing of this JSON data. We're turning it into a job object for use downstream. One interesting thing about here that we can look at is now we have, as well as output collections, we have input collections. So the previous step had sent 1.8 billion elements to this transform. However, in terms of our output, there is some data missing. So we can see that the value for output is smaller than the value for input. Okay, so this is an interesting data point. So something obviously is removing data elements within this transform. If I click on this, it's expanded. And here we can see that the transform has two branches coming from it. Before we had these two with read clickstream, we were doing p.apply twice, so we're creating a branch. Here, a single transform is outputting two values. So this tells me that this is a multi-output transform. In Java, this would use those tuple tag objects to do that. There are two outputs coming out from here. On the right-hand side, we can actually see in the output collection two outputs. And one nicety of the UI, if I hover over this value, it's turned blue. If you look at the screen where we have our transform, you notice that is now blue as well. So if I go to the other one, we can see the other one changes. So this allows me to track that this out.1, this value, which is 829,000, is going to the dead letter sink, while the rest of the values are going out. So what is the dead letter sink? If we expand it, we see it's a BigQuery write. Now here, again, very, very important practice. If you have data that is having problems being processed, JSON's being a very good example where the JSON is malformed and therefore it won't parse. If you catch that error, rather than just write it out to the logs, actually encapsulate it with some information, some metadata, and send it to a dead letter sink where you can do the processing of it later. So this is the example that I will show. Sorry. Going to BigQuery this time, I'm going to go to the dead letter table and look at the schema. So the information I'm sending to the dead letter table contains 4 pieces of metadata. Three pieces of metadata and the data itself. Sorry. Transform, error, timestamp, and data. So if I look at the preview of this, we can actually see the transform that this data came from, the particular error that was thrown, in this particular case, no store found for ID 301, and the raw data and a timestamp. So this is information that's come from various parts of the pipeline. If I look at the, run a query here to just get the head of the timestamp descending, essentially the last few elements. As I said before, I was injecting a bad element into the pipeline all the time, and this is our bad element. So this is the one that is failing to parse, showing a little bit of my age there based on a sci-fi reference from quite a while ago. Going back to the Dataflow pipeline, so the useful thing here is that we can reuse this across all of the areas that may need a dead letter. And with that wrapping that we do of the data object and the transforms, we can still track down where the problem occurred and look for fixes without having to write code every single time we want to do a dead letter sync. So here we had these two outputs. The good data, the data that was able to be parsed, is being sent to be cleansed. In this case, the clean data, that should actually say cleansed data, I guess, rather than clean data. But here, if we expand this, again, there are multiple steps involved in cleaning the data. One of them is to validate the click event. And then there are 3 outputs coming from here. This one presumably is when things are validated okay and don't need any further processing. The other 2 are going to services. Let's see what this one does. If we go and look at the name, attach UID based on, so there is some missing information that we may be able to fix for this particular element. So that's what we're doing here. This particular pattern is actually, this version of the retail app contained this pattern in this way where we are sending problem A to one transform and problem B to another transform. This is actually not a great pattern. So I would consider this to be a bug in the patterns here. In the code that we have in the repo, we've actually changed this. The reason this is not a great pattern is this makes the assumption that the problems that you have with the data are mutually exclusive. So, for example, this event has A missing, this event has B missing, and we can deal with them differently. But what if A and B were both missing from the event? This pattern would not be able to solve that problem. A better pattern, which we use later on, is actually these transforms become sequential. So rather than sending the problem to each individual transform, we just have a chain of transforms that are doing fixes. The downside to that is you need to read the element and then skip, because it doesn't contain the problem that you have. However, that's not as big a downside as we would think, because as Dave mentioned earlier, the fusion that is part of the runner fuses those sequential steps together anyway. So we're not having to materialize data. So we will end up with a nice abstraction where data can flow through and get corrected as it goes through the patterns. I will leave that open, and below we see some bad coding by me. Here we have not named these transforms. So without looking at the code, all I know is that this is doing a mapping. This is the function that was called, but because I haven't named it, I don't know what this is actually doing without going back and doing code. So that would be a doc bug, I guess, in this context. There is one other piece to show in terms of how data gets joined, and that is the, I'm going to go to transactions, processing transaction, click on that. We should see a lot of similarities to what we did before. So the transaction stream, again, is reading from Pubsub, but we notice the JSON util, and if I expand that, the same dead letter sync. So code reuse is in place here. When we're doing similar things, we're not having to replicate what we're writing. One thing that I did want to show was in this particular transaction piece, we are enriching transaction with store location. Here we are using a side input. So slowly moving side input is a very common pattern. If you look on the Apache Beam site for patterns, if you look up slowly changing side input, it's where you have a bounded sort of data as a lookup table that occasionally changes, and you bring that into the pipeline. Now, if I look at my transaction, I know this because the object that's coming from there is a P collection view. So here we have this side input that is reading from a bounded source of data. Up until now, everything has been unbounded. So this is reading from a bounded source of data, and it is processing in this transaction. The final piece that I wanted to cover, which is also a good debug tool, going back to our transactions. Until now, we haven't done any windowing because everything we've been doing, cleaning the data, parsing it, etc., can be done element-wise. So every element going in gets a mapping function and has some work done against it. Here, in this final step, we have some aggregation. So here we're doing a combination, combining. So we are counting the number of products coming in. And here we see our first window. So we see a window into, followed by a combiner. An interesting thing about the Beam model is when you do window into, the windowing doesn't actually happen at that transform stage. That's tagging everything that needs to be within the right windows. The actual aggregation based on the windows happens during the combined stage. So a good thing, and there's a nice graphic in the pattern in the Apache Beam website to show that. The other useful thing about this is looking at the reduction. So input collection going into this is 1 billion values. It's reduced by 1/3. Not surprising, we're windowing into a temporal time. So let's say 5 seconds or 10 seconds. And therefore, no matter how many value elements we have going into those 10 seconds, we're only going to get one out. So we have reduced the number of elements, but more importantly, we've actually removed data as well. And I know that because we've lost the estimated size. The size of the bytes has reduced disproportionately to the number of elements that's been reduced. So that I know that we've actually thrown some information that we didn't need away from the objects that we were processing. Okay, so this is, we've gone in very good detail on the UI, and hopefully you can see how it is a very useful debug tool. The numbers are very useful when you think you've applied something. I've done this way. You think you've applied the right windowing, and you look at the numbers, and they're like totally out of whack with the windowing that you you will expect. Those are the kind of things that really help in diagnosing issues. Let's go on to the job metrics. So here we're actually seeing metrics around the work. So we're getting into the monitoring side of things. The first few graphs, data freshness, this is how far we are, what's the latest watermark that we've seen within the pipeline. Then system latency. System latency is a very good one to put an alert against. So system latency is how long an element has been waiting around to be processed within a source. And if that's going up, it's a good one to put an alert against, because usually it means there's some issue going on somewhere either within the pipeline, or maybe one of the sinks or sources is having some issues. And then we have our auto-scaling. In this case, it's not particularly interesting on this graph because we've managed to maintain the 500 elements per second in and out of the system with a couple of CPUs. We then have the throughput graph. Now, the throughput graph is something that you will definitely spend a lot of time, especially if you're doing performance troubleshooting. It gives you a list of all of the all of the PARDUs that exist within the pipeline, along with values. And this, you can highlight them individually, and we can also sort them. So I can put them by the highest. And when you click on them, you can actually see the values. Let's actually increase. So here we're looking at 6 hours of data by default. Let's change this to max time. So now I have access to all of the data throughout the history of this pipeline, which has been running for a good long time. This funny data pattern is my injector. It cycles weekly. So you'll see small amounts starting on Monday and then getting to a crescendo before it restarts. This is getting up to like 300-400 messages a second. By selecting these values, we can actually see the pattern for that particular PARDU. Another very useful feature that was added to the UI is the ability to actually pin to a specific time slice. So if I move this, I don't know what you call this widget, but anyway, if I move this to a current location, if you notice the values changed. So the values are now showing what it was on that particular timeline. So Friday the 14th, we can actually see what those values were. This is particularly useful when if I scroll down, and one of the graphs which doesn't have any values for this particular retail application is the worker error log count. So as errors are happening within the system, you'll actually see a graph here. So when you see big jumps, and especially if you think it's something to do with performance, either with a system outside of Dataflow, for example, you're writing to a database or you're reading from it, something like that, and you look at these values, you can correlate them within the do function, and that allows you to correlate the events together in a very nice way with this visual. Another thing that's useful, if I scroll down, we have input metrics. This is bringing in Pubsub along with Dataflow information. If I scroll down here, for example, there's this cluster of increased value. By selecting and dragging my mouse across those values, I actually get the whole graph to redraw across that period. So super useful here within the context, again, of Dataflow. With the new additions, so the graphs you're seeing here are newer. These are the input metrics from an external system. Currently, only Pubsub is supported, but given this is a drop-down, I'm assuming that a lot more is coming. But if you wanted to bring in even more of the services, for that we could use Stackdriver. So Stackdriver is integrated tightly with Dataflow. Oh, yes?
Sorry, Reza. Yes, there's a question from Angeline. If you can actually describe again what data freshness metric means, what it's about.
Oh, yes. Okay, so let me quickly go back and let's go through. Yes. So data freshness is the most recent watermark, and thank you for that question. It's a good one. If you notice, the value is bouncing around here up to 80 seconds or 60 seconds. So what is a watermark now? Watermarks can have an entire 3-hour conversation with some of our data engineering technical leads. There are a couple of chapters on books on them, so I won't go into the full details. I must admit, even I have new insights into watermarks as I learn more. But essentially, a watermark, I think one of the best descriptions I heard was it's the understanding that We've processed all the data that we're aware of up to that point. And any data coming after is essentially becoming late data. And now there is much more fine-grained descriptions of that. But one of the things that's important when understanding the data freshness and the watermark is the watermark is per stage in the pipeline. It is not just across the whole pipeline. And for that, I actually did have a couple of slides on this because it is something that comes up quite a lot. And this slide helped me when I was first learning about watermarks. So the thing with watermarks is they are per stage. So if we look at our original graph, there will be an input and output per stage of the input watermark and the output watermark. For stages C and D in this graph, the watermark, the input watermark for C is the output watermark from A, and the input watermark for D is the output watermark from B. When we get to E, the output, the input watermark to E is actually the oldest of the ones coming from C or D. So whichever one of those is oldest is now becomes the input watermark for E. And that makes sense, right? Because we're working, but the intuition here is that this is all in stages within the pipeline. And then we have our final one, F, which is the takes the output watermark from E because there is only one, and go on and so forth. So if I look at my pipeline right now, I go back. Where are we? There we go. And I collapse some of these stages to make things a little bit neater. Bear with me. Now this is going to be a little bit hard to demo, but if I click on this side, because you've got to catch it at the right moment. So the read transaction, no, actually, let's start with the click stream. So the read click stream, the data watermark here is 1444. If I click over here, yes, we have 1453. So we can see these two stages. This stage is behind this stage because not all of the processing for that particular stage has completed. The watermark hasn't moved on for this stage compared to this particular stage. Again, yeah, watermarks can be, there's actually, I think, a good section on them in the streaming book by Reuven and Tyler, who are some of the original founders of Apache Beam. I think there's a good few talks around watermarks as well. That's worth saying, because you know, there's differences between watermarks on the trailing edge and the leading edge. Dataflow actually uses the trailing edge watermark, which is the oldest value, and there's some really interesting reasons why it chooses that as a watermark. So hopefully I helped explain a little bit, or maybe I just confused more with my poor explanation of that. So where were we? The last stage, yes, we were at the Stackdriver. So with Stackdriver, we have more services that we can bring in. That particular pipeline, although we didn't cover it, also wrote to Bigtable, so we can actually see some of the metrics on Bigtable. If we haven't given Bigtable enough nodes, for example, we would see this metric rise, and that would be back pressure against the system. And also that custom counter, that JSON parser, we can have that here and attach an alert to it. So this gives us a way from within the pipeline to create alerts based on values that we're updating to our monitoring system. So I have gone quite over, so I will stop there. And Dave, do you want to now pick up on the other side of things?